Section 20.1 Crystal Field Theory. Subsection I, the Irving-Williams series. We're going to look at the formation constant K sub F for this type of reactions. So this transition metal is bonded to N aqua ligands. Now L is going to replace one of the water ligands. And L has to be able to replace a water molecule for comparison. So now you're looking at the logarithm of this formation constant for a series of metals. There are two different ligands. You can see this is oxalato ligand, and this comes from glycine, glycinate, and then glycinato. So if you look at the trend from left to right, the Kf increases. And then finally a drop at zinc. The red circles are showing us the same trend. It keeps going up, and then over here there's a sudden drop. We can explain this by looking at the ionic radius of these metals. Barium, strontium, calcium, magnesium. They are all in the second column of the periodic table. So from barium to magnesium, the ionic radius decreases. Therefore, from here to here, we have stronger and stronger interaction between the metal and the ligands. Obviously, these four are not transition metals, but still we can make legitimate comparisons. And then from magnesium all the way to zinc, again, we observe the decrease of the ionic radius causes the increase of this formation constant, except for zinc. We're going to talk about zinc later. But from magnesium to copper, we see the value of K sub F increases from here to here and from here to here. Again, we have two different ligands. Therefore, we have two different series over here. But they show the same trend. When the ionic radius decreases, this K sub F increases. This is the so-called Irving-Williams series. Barium, strontium, calcium, magnesium, manganese. This is iron, cobalt, nickel, copper, and zinc. So from barium to copper, it keeps going up because the ionic radius decreases from left to right. And especially for this copper 2+, you can see it increases sharply from 6 to 8. So from here to here, the value of K sub S differ by a factor of more than 100. And over here, more than it's hard to tell. I think more than a factor of 5, roughly. So that means copper 2+ complex is particularly stable. This is due to the Jahn-Teller effect. Again, when you have copper 2+, there are 9 d electrons. So you'll have to put 6 electrons in the T2G orbitals and 3 electrons in the EG orbitals. And then that will split the EG orbitals in energy. The dx squared minus y squared orbital will be bumped up. The dz squared orbital will be bumped down. Now you have 2 electrons occupying the lower energy dz squared orbital and only 1 electron occupying the higher energy dx squared minus y squared orbital. So this is called Jahn-Teller effect that effectively reduce the energy of the transition metal complex. Therefore, this K sub F for copper 2 is particularly large. Now let's get back to zinc. Well, zinc 2+, although has a very small ionic radius, smaller than copper 2+, smaller than nickel 2+. However, in zinc 2+, we have a D10 electron configuration. So there's 0 LFSE. There's 0 ligand field stabilization energy. And also compared to copper 2+, there's no Jahn-Teller effect at all in zinc 2+ transition metal complex. Therefore, the formation constant of this zinc 2+ is smaller than that of copper 2+, and also smaller than that of nickel 2+. This trend is more obvious when you have strong field ligand, because when you have strong field ligands bonded to the transition metal, the LFSE is more significant. The ligand field stabilization energy is more significant. So again, I want to just summarize here. Mostly, if you look at this Irving-Williams series, we're looking at the trend of ionic radius. The ionic radius decreases from left to right. And then you see all those less than sign here. They are referring to the formation constant. And then over here, there's a greater than sign. This is only because zinc 2 plus, although with a very small ionic radius, zinc 2 plus does not have any LFSE. It does not have any Jahn-Teller effect. That's why the formation constant of zinc 2 plus is going to be smaller than copper 2 plus, or even smaller than nickel 2 plus. Copper 2 plus. In copper 2 plus transition metal complex, you need to realize that there are 3 electrons in the high energy Eg orbitals. Okay, 3 electrons in the higher energy Eg orbitals. In nickel 2 plus, there are only 2 electrons that occupy the higher energy Eg orbitals. But again, in copper 2 plus, it's actually no longer octahedral, it's tetragonal, and that means the Eg orbitals are no longer Eg orbitals. The 2 Eg orbitals now split into 2 different energy levels. The higher energy level, dx squared minus y squared, contains only 1 electron. The lower energy dg squared orbital contains 2 electrons. So because of that, because of this so-called Jahn-Teller effect, this copper 2 plus transition metal complex has a larger formation constant than nickel 2 plus, especially when the ligand effect, when you have strong field ligands bonded to this transition metal centers.